Welcome to a lesson on determining if a table of values represents a linear function. Let's begin by talking about the rate of change between 2 points. Given any 2 points x sub 1, y sub 1, and x sub 2, y sub 2, the rate of change between the points on the interval x sub 1 to x sub 2 is determined by computing the following ratio. The rate of change is equal to, in general, the change in output divided by the change in input, where if we have x and y coordinates, we can say the rate of change is equal to the change of y divided by the change of x, where we can use this Greek letter delta to represent change. So to find the change of y, we find the difference of the y coordinates, which would be y sub 2 minus y sub 1, and to determine the change of x, we determine the difference of the x coordinates, which would be x sub 2 minus x sub 1. But the variables won't always be x and y, so it's important to recognize the inputs would be the first values in the ordered pairs, and the outputs would be the second values in the ordered pairs. Now that we know how to find the rate of change between 2 points, if a function is linear, then the rate of change will be the same between any pair of points. This constant rate of change is the slope of a linear function. So looking at example 1, we're asked to determine if the function given by the table is linear by computing the rate of change between several pairs of points. If it is linear, give the slope. And to keep things organized, we're going to use a table like this, where the first row is going to be the change in output, or the change in y. The second row will be the change in input, or the change of x. And the final row will be for the rate of change, which is, again, the change in the output divided by the change in the input. So we'll use this first column to determine the rate of change given by this ordered pair and this ordered pair, or this point and this point. And then we'll use this column to determine the rate of change between this point and this point. We'll use the third column to determine the rate of change between this point and this point. And finally, we'll use this last column to determine the rate of change between this point and this point. Let's do this on the next slide, where I've already worked some of this out. So we'll first focus on these 2 points given by these 2 ordered pairs. So let's first determine the change of y, which is given here. The change of y is going to be negative 38 minus negative 74, which equals 36. The change of x is going to be 2 minus negative 1, which equals positive 3. And therefore, the rate of change between these first 2 points is equal to the change of y divided by the change of x, which is 36 divided by 3, which equals 12. Now as we continue on, if the rate of change in this last row is always 12, then we'll say this table is a linear function. If we get a rate of change that's not 12, then the table would not be a linear function. So for the next column, we'll determine the rate of change using these 2 points, or these 2 ordered pairs, and we'll place the information here. So the change of y is 34 minus negative 38, which is 72. The change of x is 8 minus 2, which equals 6. And therefore the rate of change is 72 divided by 6, which equals 12. So far, so good. The next column, we'll use these 2 points and determine the rate of change. And I've already shown this here. Notice how the change of y is 48, change of x is 4, the rate of change is 12. And then finally for the last column, we'll use these 2 points, or these 2 ordered pairs. Again, it's already here. The change of y is equal to 132. Change of x is equal to 11. The rate of change is equal to 132 divided by 11, which is 12. So notice how, looking at the table, the rates of change between several of the points is 12, and therefore the rate of change is the same, so we have a linear function. So we have a linear function and the slope equals 12. To check to see if we do have a linear function graphically, we could plot these points in the Cartesian plane, which I've already done to save time. So here are the 5 points on the Cartesian plane, and notice how we could graph a line that would pass through all 5 points which is the graphical verification, we do have a linear function. Now the next two examples will do exactly the same way. The only difference is, notice how the input is n and the output is t of n. And so in our table, the change in output is the change in t of n, the change in input is equal to the change in n, and we still have the same ratio to determine the rate of change. So using the first 2 points in the table, the change in the output, or the change of t of n, is equal to 29 minus 2, which equals 27. The change in n is equal to -2 minus -5, which is +3, and therefore the rate of change between these first 2 points is 27 divided by 3, which equals 9. Next, we'll determine the rate of change using these 2 points, or these two ordered pairs. So the change in the output, or the change in t of n, is 114 minus 29, which equals 85. The change in the input, the change of n, is equal to 3 minus -2, which equals 5. Notice how between these 2 points, the rate of change is 85 divided by 5, which equals 17. So we can actually stop here because notice how the rates of change are not the same here, and therefore this is not a linear function. If we did want to continue, I've also provided that work here. Using these 2 points, the change in t of n is 23, the change in n is 1, and therefore the rate of change is equal to 23. Using these 2 points, the change of t of n is 385, the change in n is 11, the rate of change is 35. Notice how for this function, the rate of change is increasing as the inputs, or n, increases. So this is not a linear function. If we did look at this graphically by plotting the points on the Cartesian plane, it would look like this. Notice how we cannot sketch a line that would pass through all 5 points, which is another verification this is not a linear function. Now let's look at our last example. Table C, notice how the input is x and the output is h of x. So we determine the rate of change between these 2 points. So the change in the output is equal to the change in h of x, which is 34 minus 90, which equals -56. The change in the input would be the change in x, which is 3 minus -4, which is 7. So the rate of change is -56 divided by 7, which equals -8. Continuing, we now determine the rate of change between these 2 points, which I've already done here. Notice how the change in h of x is -16, the change in x is 2, the rate of change is -8. So far the rate of change is the same. Using these 2 points, the change in the output, or the change of h of x, equals -24. The change of x is 3, the rate of change is -8. And then finally using these 2 points, the change in h of x is -24, the change in x is 3, and the rate of change again is -8. So -24, 3, and -8. So because the rates of change are the same for several pairs of points in the table, we can assume the function is linear. So we have a linear function, and the slope is -8. To verify this graphically, we can plot these points on the Cartesian plane, which I've done here, and notice how it is possible to graph a line that would pass through all 5 points, which verifies the table does represent a linear function. I hope you found this helpful.